Stanford University.
Okay, let's get back to the Schwarzschild metric. Carl Schwarzschild. I don't know too much about him. He was before my time. But I know his metric. I know his metric really well. It's one of the few equations that I have permanently fixed in my head. So let's write it down, and I want to simplify it a little bit for you by just rescaling the coordinates. Let's write it down first, and I'm going to write it down with the radius variable and the time variable. I'm going to put little primes over them. The primes, the purpose of the primes is just so after I rescale variables, I don't have to put primes in. I want to minimize the number of little symbols that I write down. And so to begin with, I'm going to write the metric in coordinates r prime and t prime. No difference. Same thing as last time, except just a slight change of notation. We'll write that d tau squared, that's the proper time, is equal to 1 minus 2mg, and I'm going to write r prime here. Can everybody see the prime? dt prime squared minus the r prime squared divided by this same thing, 1 minus 2mg over r prime, and then plus r squared times the metric of a unit two-sphere. Two-sphere just means the two-dimensional surface of a sphere. What was it? It was d theta squared plus cosine squared theta d phi squared. Now, first of all, the first simplification I will make is we'll just remember that the Schwarzschild radius, the radius of the horizon, the place where this coefficient function here becomes 0, is at r prime equals 2mg. So 2mg is the Schwarzschild radius. It is the radius of the horizon of the black hole. So let's give it a new name. 2mg is just r Schwarzschild. 2mg is just r Schwarzschild. Okay? And now I simply want to do something very simple. I'm going to redefine or rescale r. I'm going to define r to be r prime divided by r Schwarzschild. Now normally r's have units of length. Okay. When I divide two lengths, I get something which is dimensionless. So now my r, which is not the same r that I used last time, r prime is the r from last time, but now my r is dimensionless, and I can rewrite this. Oh, one other, sorry, we're going to do the same thing with t. We're going to write that t, what are the units of t? Time, right? But if the speed of light is equal to 1, which we're always assuming, c equals 1, then the units of time and the units of length are the same, meters or whatever. Okay, and I also want to turn t into something dimensionless, so I'm going to do the same thing, t prime divided by the same r Schwarzschild. R Schwarzschild is both a distance and a time. If you want to know in what sense it's a time, it's just the time that it takes a light ray to go the distance of one Schwarzschild radius. Okay, so now let's rewrite this metric here. First of all, 1 minus r Schwarzschild over r prime, that's just 1 minus 1 over r. Same thing. R Schwarzschild over r prime, that's just 1 over r. Now, dt prime squared, let's look at that equation for a minute. That's dt squared times r Schwarzschild squared. All right, so that's the first term. Next term, minus, Now, the thing in the denominator is exactly the same thing as in the numerator over here. So it's again 1 minus 1 over r. And now we have dr prime squared. R prime is r times r Schwarzschild. So this is just dr squared times again r Schwarzschild squared. And what about the last term here? The last term is plus. This should be prime. This should be r prime squared. R prime, again, is r times r Schwarzschild. So this is, again, r squared d omega squared times, again, r Schwarzschild squared. So the Schwarzschild radius, or the square of it, just factors out from everything. Let's put it on the outside. Put a big bracket around it. And that is d tau squared. All you have to remember is this simplified version. Of course, what is this? What appears in the brackets? That is the metric that we would have written down if 2mg was equal to 1. If 2mg happened to have been equal to 1, we would have written down this in the first place. What we find out from this exercise is that basically the metric of all Schwarzschild black holes is the same, except for an overall factor which is proportional to the square of the radius of the black hole. In other words, everything in here is dimensionless, carries no dimensions, no meters or anything else. All of the dimensions are in here, r Schwarzschild squared. And for most purposes, in studying the geometry of the black hole, really we can just set r Schwarzschild equal to 1. You know what it's like? It's like studying the metric of a sphere of different sizes. The metric of a sphere, of all spheres, is the same, except that bigger spheres and smaller spheres, we simply have to multiply by the square of the radius of the sphere. But other than that, all spheres are the same. Well, all Schwarzschild black holes are the same, except for this overall factor here. So from now on, we're going to, at least for the most part tonight, we're going to be just writing this thing down over here. It makes things a little bit easier.
Should that last term have a minus sign?
Yeah, probably, yes. Good. All right, let's address a question that we haven't asked before.
Why does that have a minus sign? If the top didn't? Should the top have a minus sign?
Hmm? Say it again?
Yes. Should the top also have a minus sign?
Yes, it should.
Yes. Okay.
All right, so what about the curvature? You remember the old curvature tensor. Curvature tensor is the thing which tells us that the space-time is not flat. I told you that it's analogous to tidal forces, the tendency for the geometry to distort objects. And indeed it is. In fact, tidal forces are curvature. How big are the components of the curvature tensor, let's say, near the horizon? The horizon corresponds to r equals 1. All right? Well, the first question is, what are the units of curvature? So let's just go back. I'm just going to, I realize you probably don't remember the formula for the curvature. I'll just very briefly remind you what it looks like. But the main thing is to read off from it its units. That's all we want. All right, the metric tensor g mu nu, that doesn't carry any dimensions. Normally it's the dx mu, dx nu. These things have length, units of length. And so this is supposed to be the square of some length, the square of some distance. And so g mu nu is a thing that doesn't carry any units at all. It's dimensionless. Now, let's go back. Remember the Christoffel symbols. I'm not going to write the Christoffel symbols in any detail. I'm just going to remind you that they contain derivatives of g with respect to x. They also have g inverses here. But g is dimensionless, and g inverse is dimensionless. So what are the units of a Christoffel symbol? They're 1 over length. G is dimensionless. X carries units of length. And so the Christoffel symbol has units of inverse length. Now, if you remember, if you don't, I'll tell you now, the curvature tensor contains two kinds of terms. It contains derivatives of the Christoffel symbol, and it contains Christoffel symbol squared. Don't try to remember the formula. It's not important. This term will have units of 1 over length squared. If I differentiate the Christoffel symbol, which already has units of 1 over length, then this has units of 1 over length squared. But so does this. If the Christoffel symbol has units of 1 over length, then the square of this Christoffel symbol has units of 1 over length. So the units of curvature, the units of the curvature tensor, usually write it, the square bracket stands for units of. The units of the curvature tensor are 1 over length squared, 1 over meters squared. And now come back. Let's ask, at any given distance, at any given r, in particular, where is the horizon in these units? The horizon in these units is at r equals 1. Let's ask, what is the curvature at r equals 1? At r equals 1, the only quantity in the metric here which has units of length is r Schwarzschild. The only possibility is that the curvature is going to be proportional to the inverse of the Schwarzschild radius squared. The only possible formula that you could possibly get by doing all the derivatives and everything else, since our Schwarzschild is the only thing with any units in here. So the curvature at the horizon, let's call it horizon, is the numerical number in front of it is not important. The curvature at the horizon is approximately equal to 1 over the Schwarzschild radius squared. As you move around in the black hole geometry, the curvature at the horizon will always be 1 over Schwarzschild squared times something which may depend on where you are. For example, at r equals, instead of r equals 1, go to r equals a half. If you go to r equals a half, the curvature will still be proportional to the same thing, but in fact it will be bigger, numerically bigger, maybe twice as big or something like that. It's not easy to read off. And as you go to r equals 0, that's where the singularity is, the curvature becomes infinite. But at the horizon, at r equals 1, curvature is 1 over r squared. The meaning of that is the curvature, for the bigger the black hole, the more massive it is. Remember, r Schwarzschild is proportional to the mass of the black hole. The bigger the mass, the bigger the Schwarzschild radius, and the smaller the curvature at the horizon. So the tidal forces associated with a big black hole at the horizon, the tidal forces associated with a large black hole are less severe than the tidal forces at a small black hole. A small black hole is a much worse, nasty thing near the horizon than a very big black hole. All right, that's one observation that you read off directly from this, that the bigger the black hole, the more massive, the less curved it is at any particular r. Next. Now let's concentrate on this geometry. Let's throw away this r squared here. It's there, but let's concentrate on on the geometry of a unit black hole, or a black hole for which you have set 2mg equal to 1. Let's concentrate on that and study that a little bit. Okay, so let's we'll go back to something we talked about last time. We'll go back to something we talked about last time. I more or less outlined for you, but let's do it again. Let's ask for, I want a new coordinate now. Now I apologize for the fact that we keep changing coordinates, but that's what relativity is all about, is changing coordinates. Okay, we're going to introduce a new coordinate to replace r. R is going to be replaced. Let's draw the r-axis, and somewhere is r equals 1. Here's r equals 0, and far away is far away from the black hole. R equals 1 is the horizon in these coordinates. All right, it is the horizon. So right over here is the horizon. And I want to invent a new coordinate which is just distance, proper distance from the horizon. Distance measured from the horizon. All right, how do we calculate the distance from the horizon? Let's go back to this formula up here. Remember that d tau squared is proper time. ds squared is proper distance, and these are just equal to minus each other. D tau squared and ds squared are minus each other. Proper distance is the same formula but with plus signs here. And now let's move a little bit away from the horizon, radially outward, and ask, let's take a little differential distance away from the horizon here. No, not a little bit. Let's just take some differential distance over here and ask what the proper distance between these 2 points is. The proper distance between those 2 points is just ds. Now, I'm moving radially outward. Here's my black hole. I'm moving from here radially outward, and I'm asking how much distance that corresponds to. But first of all, I'm moving, not literally moving, I'm just displacing a point without changing the time, first of all. Just comparing 2 points at 2 different distances from the black hole at the same time. So dt from here to here is 0. And furthermore, I'm not changing the angle, I'm just moving radially. So d omega is equal to 0, no change in angle. And that means that ds squared is just equal to dr squared over 1 minus 1 over r. Or ds, the distance between these 2 points, is just dr, little dr, divided by the square root. I took the square root. We can also write this in another way. In fact, we can go right back to here and write it, multiply and divide by little r. This becomes little r minus 1 over r. Little r minus 1 over r, and this is also little r minus 1 over r. R upstairs. Everybody see what I did? I just wrote that 1 minus 1 over r is equal to r minus 1 over r. That's over here, and over here I just turned it upside down. Okay, so now here's my formula. I can just write it a little bit differently. Square root of r times r minus 1. Let's call the distance, the proper distance from the horizon, let's give it a name. Let's call it rho. Right? The proper distance from the horizon we'll call rho. That's not r minus 1. R minus 1 is a certain kind of distance, but it's not the proper distance from the horizon. How do we find it? Well, this is the differential displacement in distance in moving a radial distance, dr. Rho, the actual distance from the horizon, is the integral square root of r over r minus 1 dr. From where to where? This is a definite integral. Maybe we should call this prime since it's just an integration variable. Not the same prime as before. Let's just call it r. What are the limits of integration if I want to calculate the distance from the horizon to some particular point at coordinate r? I integrate from the horizon, which is 1, to the point r. I better call this prime if I don't want to abuse mathematical terminology, so I'll call this an integral over dr prime. This is some function of r. We actually count. I'll tell you what we know. You can do the integral. The integral is a doable integral, but I'm not going to do it. But I'll tell you some things about it. Okay. Rho is some function of r. Let's call it just rho of r. And what's more, the metric over here is also just a function of rho. We know the relations, a relationship between rho and r. There's a relationship between rho and r, and our favorite function over here, r minus 1 over r, that's also a function of rho. Right? Let's give it a name. Let's I'm on the wrong page. Here it is. Let's call it f of rho. Now, I'm going to cheat a little bit. That's not quite what this is. I'm also going to change the definition of t, but only in a very, very simple way, in an extremely simple way. I'm going to define, this is definition now, omega is just equal to t, I think it's divided by 2. T divided by 2. No big deal. Just for convenience, I'm going to use a variable which is the time divided by 2. Right? This is a sort of artifact of a particular original definition of time. It might have been nicer if I would have used 2t over 2, or if Schwarzschild would have used t over 2. But here it is. We're stuck with it. Omega is equal to t over 2. And let's write the metric in the form f of rho times rho squared. Now, f of rho times rho squared is just some function. The fact that I wrote it as f of rho times rho squared, no content in that yet. It's just some function of rho squared times dt squared, but dt squared I'm going to replace by d omega squared. dt squared is just 4 d omega squared. So I can absorb that extra factor of 2 right into here. I haven't really done anything. I've just used the fact that r and rho are related. If I know r, then I know rho. If I know rho, then I know r. And so I can rewrite this thing over here as a function of rho. And here I've done it somewhat arbitrarily, dividing it into a rho squared and an f of rho, for reasons that will become clear in a minute. Okay, next, what about this piece over here? This piece over here looks like it's going to be a mess, but it's not a mess. It's very simple. It is just, let's see if we'll see why in a minute. It is just minus d rho squared. Why is it minus d rho squared? The reason is because rho was defined to be proper distance. And S is defined to be proper distance. Where is it? We did the whole point of changing variable to rho. There it is. Let's take this definition of rho here. What is d rho by dr? d rho by dr is just square root of r over r minus 1. If you differentiate an integral, you just get the integrand. Now square this. d rho squared, dr squared, that's just this thing here. And now multiply by dr squared. d rho squared is precisely the thing which appears here. That was the whole point of changing variables to rho, so that this term here would just be minus d rho squared. It just measures distance along the radial direction, proper distance. Yeah.
When you have f of rho times rho squared,
Yeah.
are you essentially just defining f to be such that
Yeah.
the whole term up there looks like that?
Yes.
Okay.
So far, yes. Yes. There's no content, well, I mean, there's never going to be any content into this division, but we'll find that it's a convenience.
I think for ds, you want to reverse those signs.
Yeah, for ds squared, that's true, but I was actually writing d tau squared here. Yes, you're right. But depending on whether we write d tau squared or ds squared. Right. And what about the last term? The last term is r squared minus r squared, but r is also some function of rho. We haven't worked out what it is exactly, but it is a function of rho times the omega squared. It is possible to work out what r as a function of rho r and what rho as a function of r is, but we don't need to. It's the form of this metric, just exactly as it is here, that's interesting, plus a little bit of knowledge about what f of rho and r of rho are like. We actually worked out last time, when you're near the horizon, when you're near rho, where is the horizon in this form here? In terms of rho, what is the horizon? Rho equals 0. Because what is rho? It's the distance from the horizon. Right. So rho equals 0 is the horizon. And if you work this integral, it's not hard. Oh, sorry, it's a hard integral. But if you work it out in the vicinity of the horizon, in other words, near r equals 1, you can do that. You can approximate, and you find a simple formula. You find a number of things. First of all, you find that the limit as rho goes to infinity, large or far away, of f of rho times rho squared. Now what is that? What is that? That's basically just a coefficient function here, far away. What is the coefficient function far away? It's r minus 1 over r, which is just 1 far away. Not quite 1, because the omega squared is not quite dt squared. It differs by a factor. What you find is that this is equal to the number 4. So far away, f of rho times rho squared is just equal to 4. That just reflects the metric far from the black hole. Far from the black hole, f of rho times rho squared is just equal to 4. That's one thing. Next, limit as rho goes to 0. Rho goes to 0 is getting right up against the horizon, and it's where we're really interested, trying to find out what's going on at the horizon. F of rho is equal to 1. So close to the horizon, f of rho is just equal to 1, and you just have rho squared d omega squared. You may find that familiar. Rho squared d omega squared. We've seen that before. So close to the horizon, f of rho is just equal to 1, and we just get rho squared d omega squared. That was the reason, incidentally, for dividing it up in this way. Because close to the horizon, f of rho times rho squared is equal to just rho squared, or f just equal to 1. Now, a little more. Do we know anything else? Yeah, we know that the limit of r of rho near rho equals 0, that we can work out. What is r of rho right at rho equals 0? Rho equals 0 means at the horizon. R equals 1. 1. Right. So it's equal to 1, but we can do a little bit better. We can do a little bit better. It's plus rho squared over 4. These are really all we need to know. I'm not even sure I need to know this rho squared over 4 at the moment. I might use it. I don't remember. But this is basically the properties of everything here. Now, the most important thing is to look at this when rho is small. When rho is small, it's just rho squared d omega squared minus d rho squared. That's exactly flat space in hyperbolic polar coordinates. So let's just review for a minute hyperbolic polar coordinates. That's the light cone of flat space, okay? And rho squared, the omega squared, no, not that omega, little omega. Those are the hyperbolic coordinates, hyperbolic polar coordinates, where rho is constant along hyperboloids. This could be rho equals 1. This could be rho, in other words, all along this trajectory here, this point is 1 unit of rho away from the horizon. The horizon's right at the center, rho equals 0. This is rho equals 2, rho equals 3, rho equals 4, and so forth. And that's just looking at this metric here and noticing that apart from this f of rho, near the horizon, it just has the form of flat space in polar coordinates, hyperbolic polar coordinates. Omega, the lines of constant omega, they look like this. Omega equals 0, omega equals 1, for example, omega equals 2, omega equals 3. Where is omega equals infinity? Omega equals infinity is right along this light cone here. Omega equals infinity. Remember what omega is. Omega is just t over 2. So we've discovered some coordinates in which time is like a hyperbolic angle, and time infinity is just the light cone here. Okay, that's one fact. What about in here? In here, we talked about it last time. In here is the place. That's that's where r is less than 1. When r is less than 1, in here, r is less than 1. And when r is less than 1, the sign of these two terms interchanges. This one becomes negative, this one becomes positive. In here, rho squared is actually negative, less than 0. In here, rho squared is less than 0. Let's see, can we see that? Yeah. Yeah. When rho squared is positive, r is greater than 1. That means outside the horizon. When rho squared is negative, to get behind the horizon, you want r to be less than 1, and that's rho squared equals negative. Okay, so behind the horizon is in here, rho squared negative. And the lines of constant rho in here look like that. The lines of constant omega, they're still angles, they look like this. Nothing crazy is going on here. Space has not become time, time has not become space. We've just introduced coordinates which have a funny property that when you go from here to here, what was space-like out here becomes time-like in here. It's a complete coordinate artifact. And yet, there's something interesting about it. Okay. If we go far away, we have to remember that f of rho is not just 1. Right? F of rho is not just 1, and so that means the metric along this omega direction here, that's what this is, f of rho times rho squared, it does differ from flat space. It does differ from flat space, but the differences show up in the way f of rho varies as you move away from the black hole, and the way this thing varies. Close to the black hole, though, this is what the geometry looks like. Now, this was rho equals 0, but r equals 1. What happens as we move up into here? What happens as we move up into here is that r decreases. Rho squared is negative in that region. So as we move into this region, r gets smaller and smaller and smaller. We get 1 plus a negative quantity. And as that negative quantity increases, r gets smaller and smaller. Eventually, we hit the point, the nasty point, where r is equal to 0. That is a nasty point. That is not just a coordinate glitch. R equals 0. Is over here. It's a hyperboloid in these coordinates. And if we were to calculate the curvature, it's not too hard to believe. What's happening here? As r goes to 0, the sphere is getting smaller and smaller and smaller. Curvature is getting larger and larger. As we move toward this point here, the curvature becomes bigger and bigger, and in fact becomes infinite on the green line here. This is a true singularity. It's a place of infinite tidal forces, and no, it's basically a place you wouldn't want to be. The problem with it is you can't avoid it. It's not really a place, as we discussed last time. It's not really a place. It's really, in a sense, a time. So imagine finding yourself over here somehow. Let's not go there yet. Here's the black hole. Here's an orbiting space station far away. Where is that? That's very far away. It's out here. It's out here. It's at r equals 100,000, 100 or a million. That's way, way out here. And as long as you don't do anything stupid, namely jump off or allow yourself to get sucked in by gravity, you're safe enough out here. Nothing bad will happen to you. But if you're foolish enough to go and say, I want to explore what's in here, long in the past jump off the space station and fly in here, you might find yourself in there. If you find yourself in there, you're cooked. There's no way out. You can't get out. You've passed a point where in order to get out, you have to exceed the speed of light. The speed of light corresponds to 45-degree lines in this diagram, or light cones. Light cones are 45-degree cones. And so the best you can do in trying to escape is this dotted line here, no matter what you do. And so inevitably, you're going to hit the singularity. Once you're behind there, there's no choice. No matter how hard you try to accelerate from here, unless you can exceed the speed of light, which I assume you cannot, you're going to wind up hitting the singularity. And so you're stuck. Where is the point of no return? The point of no return is right over here. That light cone. What is that light cone? Well, each one of these hyperboloids is a different value of rho. Rho equals 4, rho equals 3, rho equals 2, rho equals 1. What is this one? What is this point right over here? Rho equals 0, right? But rho is equal to 0 all along, well, just imagine a hyperboloid very, very close to here. Essentially all along this line here and this line, rho is equal to 0. Rho equals, let's say rho equals epsilon. Rho equals a tiny, tiny number. Rho equals a tiny number is a hyperboloid very, very close to here. There's something very different about this kind of geometry than ordinary geometry. If I drew ordinary geometry and I said, where is the point r equals 0? Well, we know where that is. That's right over here, right? Where is the point r equals some tiny number? Well, it's not a point. It's a tiny little circle. But that circle gets closer and closer to the center as I make the distance smaller and smaller. Quite different than here. Where is rho equals something tiny? It's this whole hyperboloid here. As rho gets smaller and smaller, it tends to the light cone here, not just to this point. The meaning of that, and what was rho equals 0? Rho equals 0 was the horizon. So the horizon is not just this point at the center. The horizon is all along this line here. Anybody who finds himself beyond this point is inside the black hole, is at r less than 1, inside the interior of the horizon. And as you can see, just looking at the diagram, they're doomed. They can't get out. They're going to hit the singularity. So the point of no return is indeed rho equals 0, but it's not this point. It's this whole line. This whole thing is the horizon of the black hole. And once you pass it, you've passed the point of no return, and you're doomed. Any questions now?
That looks like hyperbolas that are...
Don't tell my wife.
I didn't want to say. Shut down the
I
video.
hope she's not watching.
How many calories are in this?
Well, what's that?
I'm going to ask. This was last week.
These sort of, I guess, horizontally oriented, like bowls, hyperbolas, are those still constant rho?
Yes, they are. Right, but there are places where rho squared is negative. They're imaginary values of rho, if you like. There are places where r is less than 1. Rho and r are functionally connected. If you know r, you know rho. If you know rho, you know r. Okay, so these are also lines of constant r. But they're real, they're perfectly good values of r, but they're less than 1. And the red lines are lines of constant t. They don't look like it, but they are. Okay. Okay. These coordinates, the coordinates that I've constructed over here, have a name. They're called Kruskal coordinates. I'll tell you the history. Maybe I should spend 5 minutes telling you the history of black hole physics. When Schwarzschild wrote down the Schwarzschild metric, he didn't know that the horizon was a horizon. As far as he could tell, and Einstein and all the people who studied these things for a while, the r equals 1 was a nasty singular place. They looked at this function and they said, oh dear, this is divergent at r equals 1. Something bad is happening there. And so the conclusion was that the horizon was a bad place. It took...
The vertical axis of your diagram, W. What's the vertical axis? Is that time or is that...
It is a time variable, but it's not the same time that occurs up in there. The time that occurs up there is the one which evolves along here.
So whose reference frame does these axes correspond to?
It's a reference frame of an infalling observer, as opposed to somebody who stays outside the black hole. Somebody who stays outside the black hole lives on one of these hyperboloids. Somebody falling in, for example, might find it convenient to use rectangular coordinates in here. Right, so that's a good question, but no. So as I said, the history was at first people did not realize that that the horizon was a smooth, non-singular, ordinary place. It was sometime in the 1950s that a friend of mine, David Finkelstein, wrote down what were essentially coordinates of this type. Not exactly these coordinates, but coordinates of these type, and realized that the horizon was a point of no return and not itself a significantly dangerous place. The coordinates that he used, he invented himself, but they had been previously invented by Eddington, by Arthur Eddington, and they're known as Finkelstein or Eddington-Finkelstein coordinates. They're not exactly these. Somewhat later, a few years later, a gentleman by the name of Kruskal, who was not a relativity expert at all. He was a plasma physicist, but very good at equations and very good at changing coordinates. This was his thing. He loved to change coordinates. So somebody showed him this thing. He changed the coordinates and changed the coordinates, and eventually found these coordinates that I've indicated, where the metric has this nice form, and where the picture looks exactly like this. These are called Kruskal coordinates. Kruskal. The term for this object was, I think, I don't know what it was called, just a massive star, a collapsed star. I think it was called a collapsed star. It was John Wheeler who called it first a black hole. John Wheeler was a very nice man. He was a very sweet man. He was a good friend of mine, too. He had a kind of side to him which I didn't approve of. He had a politically very conservative side. His political conservativeness, incidentally, did not extend to social issues. His political conservativeness had to do with one thing and only one thing only. He was afraid of the Soviet Union having nuclear weapons. So he was very anti-Soviet Union, and especially anti-Soviet expansionism. And so he had this very strong politically conservative side to him, and we would argue about it, but not so much me, but some of my friends. And he was a very thoughtful and gentle and nice person. Did not have a socially conservative side to him. In fact, I remember once we were sitting in a cafe in Valparaiso, Chile, And John, he was about 85 years old, my wife, him, and he was sitting around, and he started to look very agitated. And I said, "What's the matter, John? Don't you feel well?" And he said, "No, he wants to get up and take a walk." I said, "Well, okay, you want me to take a walk?" "No, I'm going to take a walk myself." And I said, "What are you going to do, John?" He said, "I'm going to check out the bikinis." So he was not a social conservative. And in fact, when he wrote a paper, his first paper on Schwarzschild metrics, he coined the term black hole. The result of this is he had big trouble with the physical review. The physical review did not want to publish it. And the reason, I knew there was a problem. This was before my time, actually, but nevertheless, well, not quite. But I knew there had been a problem. I didn't know what it was. I thought it was just the physical review being its conservative self. But no, they were hyper-conservative. They thought that the term black hole was obscene. And so they refused to publish it at first. He fought and he fought and he fought with them. Eventually won, but then just to get back at them, his next paper was called "Black Holes Have No Hair." And it was already too late. Incidentally, what it means for black holes not to have any hair, I'll tell you what it means. If you take a non-rotating black hole, gravity is so strong that it will always pull it together so strong that eventually, after a very small amount of time, the horizon, even if it starts out being spherically very asymmetric, could be two rocks coming together, very unsymmetric, might start out looking like that. In a very small amount of time, it will pull itself into a sphere and become indistinguishable from a sphere. And John called that property, the property of not having any visible structure or any visible defects on it, he called that not having hair. So the statement that black holes have no hair is just a statement that gravity is so strong that it'll pull any black hole, the horizon of it, into a perfect sphere. If it's rotating, then the sphere can get deformed, can get into an oblate spheroid, but the nature of the oblate spheroid depends only on the angular momentum. So black holes have no hair. Okay.
Question?
Yeah.
We have rho squared equaling a negative quantity.
Mm-hmm.
How come we don't see i's, imaginary number of things going on?
No, you can put them in if you want. You could say if rho squared is negative, then rho is imaginary.
Okay. Doesn't seem to come up as a...
No, it's because normally you tend to use r. And r is rho squared. Or r minus 1 is rho squared. Or 1 minus r, one of the two of them. Okay. Now, let's talk about things falling into a black hole. A thing falling into a black hole. Incidentally, you might ask, what about the other half of this diagram down here? We're going to see that the other half of it down here has no real physical significance. We're going to come to it. For the moment, we're mainly interested in this upper right-hand part. Where is the exterior of the black hole? The exterior of the black hole is out here. The interior of the horizon is in here. Okay, so let's redraw our picture. And let's talk about somebody falling in. Falling in is Alice. Alice falls in, and let's redraw some lines on here. She falls in. Those are lines of constant r, but I'm more interested right now in lines of constant time. So here's the lines of constant time. And this one over here is t equals infinity. In other words, the horizon is t equals infinity. Very strange, but this place that you thought was a place, the horizon, really also has the character of being a time, and it's time t equals infinity, or omega equals infinity. Strictly speaking, it's omega equals infinity, but omega and t are closely connected. And so if you look at this diagram, you can see that when Alice falls in, she doesn't pass the horizon until t equals infinity. That's the sense in which a infalling object never passes the horizon. It does pass the horizon. Here it is. She went sailing right through, encountered nothing crazy there, but it's just a strange set of coordinates that says that this is t equals 0, t equals infinity. So, you might say it doesn't really mean anything to anybody, the fact that Alice never gets in. But on the other hand, here's Bob out here, and Bob is watching. Bob is watching Alice. Let's put him in a little closer. And Bob moves on. Bob is not going to go into the black hole, ever. He's going to stay out a fixed distance away, and he's going to watch Alice. And let's see what he sees about Alice. Seem to have lost my pen top. Oh well. Here he is over here. Let's put him over here. Here's Bob, and he looks back. What does look back? He looks into the past. He can't see Alice at the instant that he looks at her, that he looks. He sees Alice in the past. He sees light coming from Alice. So he sees Alice over here. Remember, light traveling on 45-degree angles. Later on, over here, he looks back again, and he sees Alice over here. He looks back again. As long as he stays outside the black hole, and he looks back, what he will see is Alice getting closer and closer to the horizon, but never passing it. So in fact, it's not just a coordinate artifact that Alice doesn't go through the horizon until t equals infinity. It's actually what Bob sees. As far as Bob is concerned, Alice never passes the horizon. If Alice, in her own frame of reference, passes the horizon, she can't send a signal to Bob to say that I've passed the horizon. So everything that Bob measures, everything that Bob cares about, everything that he can see, his entire physical observations all involve Alice outside the horizon. She gets closer and closer. So you might say then that Alice gets closer and closer, and as she gets closer and closer, all of her parts get closer and closer, and that's what she does. On the other hand, as far as she's concerned, nothing very special happens. She just goes through the horizon. Next question. What if Alice is watching Bob? Let's ask now. It's quite apparent from this diagram that when Bob watches Alice, he sees Alice slow down. Alice simply takes an infinite amount of time to get to the horizon. All of her clocks, as far as he can tell, all of her clocks just slow down and slow down and slow down. So she just seems to asymptotically slow down and approach the horizon. People generally tend to think that that must mean that if Alice is watching Bob, she sees Bob speed up. But that's not the case. She does not see Bob speed up. Here's Alice over here, and she looks back at Bob, and she doesn't see anything very special. Oh, let's put in the singularity over here. The singularity is here. That means Alice is terminated. Alice is terminated at that point. No more Alice beyond this point. Probably before she gets to that point, she's terminated, but mathematically, she's terminated over here. So she looks back, let's say from this vantage point over here, and she sees Bob. Hi, Bob. Well, Bob says hello to her. Okay. Now, a little later, she looks back, and she sees Bob again. In fact, she passes the horizon over here. Bob can no longer see her. Bob can never see her beyond this point. There's no point on Bob's trajectory here where when Bob looks back, he can see Alice. But Alice has absolutely no problem seeing Bob. So Alice sees Bob, and moreover, there's nothing that would make you think that she sees Bob speed up, and she doesn't. What does happen is there's a last point on Bob's trajectory that Alice can ever see. Alice cannot see Bob past this point. Why not? Because she's dead, that's why, okay? So there's a complete asymmetry. Bob sees Alice slow down, sees her flatten out like a pancake. Takes infinite time for her to get anywhere. Alice looks back and sees nothing special about, yeah.
So geometrically, there's some special point between the two where it looks like where she sees Bob is way in the past, right? Before
Yeah.
Bob is seeing her going to the horizon.
Everybody sees everybody else in the past.
Right. But I mean, is there a juncture where the geometry is such that it's a special point where,
Nothing special.
so according to this diagram, she's never going to see Bob while he's seeing her go across the horizon.
Right. She will never see Bob at the time when he sees her go through the horizon. But that's partly because he never sees her go through the horizon. But, right. But more than that, he can never, she can never see him after that point. So, but again, not because he's hiding or because he's accelerating, just because she's terminated.
There.
Right.
One question, is this, I mean, if I'm Bob and I understand all this general relativity and so on, but I say to myself, well, I can't see her falling in, but I know she's already fallen in, or is it?
No. There's no sense in which she has fallen in. He looks and she has not
It's
fallen
not
in.
just a matter of what he sees, it's actually in his reference frame, she doesn't ever fall in. I don't know if you see the distinction.
So can he go back and get her? Before she falls in, can he go back and get her and bring her back out?
No.
Why not?
Well, once you passed here,
No.
Well, so the question would be, what happens if there's someone following Alice in? What do they see?
what happens if somebody's following Alice? Okay, let's draw somebody following Alice. Here's somebody following Alice. That person following Alice, incidentally, I've drawn Alice as if she was moving. No, this is Alice over here. Sorry, not that. Here's somebody following Alice, right? Sees nothing special. Sees Alice over here, sees Alice over here, sees Alice over here, sees Alice over here. Nothing particular. Likewise, Alice watching, who is this fellow? Charlie? That's Charlie. Alice watching Charlie sees nothing special. Of course, both of them eventually get terminated. But if Charlie is following Alice in, nothing special at this point. It's only Bob, and this is a consequence of the fact that he's that he has to accelerate to stay outside the black hole. If Alice is falling in free fall, and Charlie is following her just behind her, they're just in free fall. They talk to each other. They can hold hands. They can have a conversation. Conversation can go back and forth. Here, Alice says something to Bob. Bob says something back to Alice. Alice says something to Bob. And of course, so did I say Bob? Yeah. I meant Charlie. Alice and Charlie have a nice conversation. Now, Alice can look back and hear Bob's half of the conversation, or maybe not hear, but in any case, see Bob's half of the conversation. But once Alice gets past this point, Bob cannot receive anything from Alice, ever. So it's completely asymmetric.
So if there was a hoop going in and then a basketball followed right after a minute, what would Bob see? He would see the hoop going in through he would see the basketball going in through the hoop? Because it's kind of getting superimposed.
I'm not sure where your basketball and your hoop are.
No, the question is, Alice goes in and Charlie follows right after a minute, let's say. What does
Alice?
Bob see? He sees,
Sorry, we have Alice, Charlie, and Bob. Who's doing what?
Alice falls in,
Yeah. Charlie follows her or not?
Charlie follows like right after.
Right.
And what does it appear to Bob on the outside? It appears,
Once they've passed the horizon, Bob doesn't see them all together.
no,
But Bob never sees either one of them.
Bob never, no, right, Bob never see, oh, I see what you're asking. Right, good. Yeah, so what it looks like to Bob is Alice, here's Charlie, and they're both moving toward the horizon. Alice is first, so she gets contracted according to him first. Charlie is still moving, he's a little bit contracted. And then a little bit later, Alice is getting squashed flat. Maybe a lot later, Alice is getting very squashed. Charlie is right behind her. And he just sees them fall in with Charlie getting closer and closer and closer, right behind her, but never catching her.
Question. We're watching them get flatter and flatter as they move towards the horizon. But isn't that the opposite of what you would guess would happen based on tidal forces? Tidal forces would tend to switch in the other direction?
Right. Remember, the bigger the black hole, we're thinking about, all right, there's an important point here. When we're talking about all of this and all of this stuff happening near the horizon, we were assuming the black hole is big enough that, or that Alice and Charlie are small enough that tidal forces don't affect them very much.
Okay, so we're not looking at tidal forces in that.
We're not looking at tidal forces, right. We're imagining a very, very big black hole. Incidentally, that black hole would have to be very big. If you took a solar mass black hole, which has a Schwarzschild radius of about 1 kilometer, it has incredibly fierce tidal forces at the horizon. It's not very big. It's not very big. You would get squeezed through like toothpaste at the horizon. But if you were to take a black hole as big as the one at the center of the galaxy, the tidal forces at the horizon would be pretty weak. If you took one which is as big as any that are known anywhere in the universe, 10 to the 9th solar masses, then an ordinary person would be small enough that they would not experience serious trouble due to tidal forces. That's what we're thinking about here. Right. You're perfectly right. The tidal forces would have the elongating effect. Yeah.
Question, from the perspective of Charlie.
Well, that, of course, is a real effect as far as Alice and Charlie are. Tidal forces, they're not deceived about. They feel them. This effect, they don't feel. Their meter sticks get squashed. Their clocks get slowed down, including their internal clocks. Their biology does exactly what's necessary for them to not experience anything at this, yeah.
Yeah, I was looking at, from Charlie's perspective, he's following, Alice going into the black hole, maybe 100 feet away or whatever, and they're communicating. Will Charlie ever see Alice go across the event horizon?
Yeah.
Even though he's outside the event horizon?
No. Well, okay, let's look at it. No. Let's, here's where you've got to draw a picture. Every question like this, draw a picture. Here's Alice going through, here's Charlie going through. Charlie is going to look at Alice. You're asking me about Charlie looking at Alice, right? Right, he looks at her here, sees her here. Looks at her here, sees her here. Looks at her here, sees her here. When does he see her pass the horizon? At exactly the same time that he passes the horizon. He sees her pass the horizon just as he passes the horizon. He looks back, okay? After he has passed the horizon, he looks back and he sees that she's inside.
What if they don't both go through at the same time?
Well, if they go through at the same time, they go through at the same time.
No, not at the same time. Not at the same time. Yeah.
Here they're not at the same, they're not going through at the same time. But of course, remember that Charlie sees Alice in the past, in his past. So Charlie Charlie visually sees her past the horizon. There's no signpost at the horizon. But if he happens to know by calculation and by being a physicist or whatever it is, if he happens to know exactly when she's going to pass the horizon, he will see her at that point at the time and at the point when he passes the horizon.
So taking that and extrapolating out, if you have like a million people separated by light years falling into the black hole, they will all, from their perspective, see each other under the event horizon at the same time.
Yeah.
That's odd.
Now, Charlie is over here. He's watching Alice. But now he decides at the very last minute, no, I don't want to follow Alice. I'm going to accelerate my way out of this black hole. And so he accelerates and stays out of the black hole. Then as he looks back, again, he never gets to see Alice cross the horizon. From this point over here, he sees her getting close to the horizon. But if he changes his mind at this point and accelerates himself out of the black hole, then he will not see Alice cross the horizon. It's only if he crosses the horizon himself that he gets to see Alice cross the horizon.
Well, of course, so let's say Alice has gone through from her perspective. And from her perspective, Charlie is still outside.
Okay.
So she sees him out there.
Yeah, she does.
Once he gets inside, once he's inside the black hole, it seems like from his perspective, he and Alice are at exactly the same radius.
Exactly the same what?
Radius. Because they went through the horizon at the same point, at the same time.
Well, Alice doesn't see Bob go through the horizon at the same time she does. She sees Bob go through the horizon when she's over here.
But then once he's through, from his perspective, they are both at the same radius, right? But from hers, they're not. She's, well, closer.
It's, the diagram says it all. The diagram says it all. If, really.
Can I suggest, as you were saying, he's looking at the past. Okay, so when he sees her, he's not looking at her present, he's just looking in the past, same as everything that we look at is always in the past.
Right.
It's always on the light cone.
Right. We never see anything at the same instant that we look.
What does the free fall path actually look like on
What
this
is-
diagram? You drew it curvy once and...
It looks almost like a straight line. Pretty much, approximately. Not exactly, but approximately. Pretty much.
Well, what if they fall through at the same point?
Then they're Democrats. Look.
Quantum mechanics apparently can unify, or string theory can unify quantum mechanics and general relativity. Can it be used to examine that R less than 1 sector?
Tough, hard. That is a very, very current question, which is being debated like mad at the present time. And let's put it this way: it is very subtle and very hard.
I have a question.
Everything depends on...
Question?
Yeah. Could you discuss Alice's clock? What happens to Alice's clock as she goes in?
Yeah, here's Alice's clock. Goes tick, 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 tick.
And how about her velocity, or does that have any meaning?
What's that?
What about her velocity in the time of travel?
In her own reference frame, her velocity is constant. And in this picture, she pretty much moves with, in her own reference frame with constant velocity. And if you measure off proper time, it'll just look like this. She's practically, yeah. This is practically flat space-time, at least near the horizon. If you don't get too near the singularity, what goes on here is pretty much close to flat space-time. So let's keep her away from the singularity. That's a little too bad. But as she falls through here, with pretty much free fall, her clock just ticks off time.
So if Bob is accelerating fast enough to not fall in a black hole, he'll never see her falling. But if he's accelerating not quite that fast, he'll cross the event horizon at the same time. So there's...
What's that?
Suppose Bob is accelerating, how would that be described in that diagram?
Here is Bob is accelerating.
But no, not that fast. He's trying to get away, but he doesn't have quite enough oomph.
Right, then he falls through. Then he falls. He might wind up falling through over here.
Right. Okay. So
Now, if he falls through late enough, if he falls through very, very late, let's suppose he falls through way out here, then he looks back, and what he sees is Alice just after she passes the horizon. He doesn't have much time. He gets terminated pretty quickly up here, and so he doesn't get to see much of Alice after she passes the horizon. He's watching her, nothing strange about her, but he gets terminated very quickly. So from Alice, well, in watching Alice, Bob will just barely see her cross the horizon, not before she gets killed, but before he gets killed.
So that means that if you're trying to accelerate to get out of the black hole, you can't quite get there. You hit the singularity sooner rather than later.
No,
It gets killed right away.
No. You have to remember that the distances and times on this diagram have to be, yeah. Okay, so that's...
Everything is assuming that nothing can cause the speed of light, right?
Nothing what?
Nothing can cause the speed of light.
Yeah, nothing can exceed the speed of light.
So far, there is absolutely no credible evidence of anything crossing the light.
No credible evidence of what?
Anything crossing the speed of light. So
There's nothing, no evidence of anything crossing the speed of light.
The media sometimes talks
What?
about I sometimes read there in media that there's some evidence of something crossing the speed of light.
In Italy, for example.
In Italy, yeah, that happened. That does happen in Italy. Yeah, we've been through this. We've spent time discussing the Italian laws of physics. It's worse in southern Italy than in northern Italy, but as soon as you cross the Alps, or going through the Mont Blanc tunnel. Well, you don't go through the Mont Blanc tunnel anymore, but.
Can I ask one more question?
Mm-hmm.
Suppose Alice and Bob are together. They have a quote, a synchronized clock, whatever that means. And Alice goes and gets very, very close to the event horizon and circles back out.
Well, if Alice makes a sudden change in her motion, it's not even clear what it means to say that their clocks are synchronized.
Agreed. So if they're in the same place and they say it's 12 o'clock, let's say.
Okay.
And then Alice says, I'm going to take a dive.
Look, you can think of a zillion questions to ask, but draw the diagram, and answer the question. You've got the tools now to answer the question yourself. I showed you how to answer a few questions, and the diagram is all you really need. Okay, if there are no other urgent questions, yes, well, okay, there are urgent questions.
If Bob manages to...
You got to speak up because I'm deaf as a stone.
I'm sorry. If Bob manages to accelerate on his original path, and I'm still not clear about what he actually sees with Alice, does he see her for an infinity of time?
Sorry, if he does or doesn't accelerate?
He does accelerate.
He does not.
He does.
He does accelerate.
He doesn't cross the event horizon.
He doesn't cross the event horizon.
But she does.
And she does.
So what I'm trying to understand is whether or not he actually sees her for an infinite amount of time. Because if that's so, then
yeah.
she never dies, right? And so from his perspective, and that's
from his perspective, he sees her for an infinite amount of time, but he sees her slow down.
Yes, of course.
He sees her slow down. He will see a finite number of heartbeats.
But her reality then is different from his reality.
Yes.
Well, I don't know what reality is. A loaded word. It's a loaded word, and we can come back to that question of what is real and what is not real, but the figure, for example, tells us there is a sense in which Bob sees Alice die. Okay? Think about it. He's watching her and he sees a finite number of heartbeats. It takes an infinite amount of time, and over that infinite amount of time, he sees a finite number of heartbeats. That means in him watching her, most of the time, her heart doesn't beat. So in some stupid sense, he might conclude that her heart, unless he said to himself, oh, I know she's crossing the horizon, but just in terms of watching her, she slows down and her heart stops. Not quite, but slows down to almost, so you might say that Bob sees Alice die at the horizon. But of course, that's to some extent just an artifact of the fact that he's accelerating away from her. She is perfectly happy until she gets near the singularity. Okay, yeah.
So from Alice's perspective, as she's falling through, until she falls through, every bit of matter in that black hole is all on the surface, right? Until she falls through.
Well, you're asking what she sees?
Yeah.
Well,
I mean, it seems like what she sees is she falls through just the same time all the other matter falls.
Exactly the same as Charlie following Alice. Charlie following Alice, until Charlie here passes the horizon, he sees Alice outside.
So she sees everything on the surface, or just about
in some sense, yeah. In some sense, yeah. Right. That's right, until she falls through. But she doesn't see anything very unusual. Charlie doesn't see anything unusual about Alice. He just sees Alice going about her business, and at the point where he crosses the horizon, remember, nothing special happens when he crosses the horizon. There's no signpost there. He just goes on his merry way, she goes on her merry way, and he sees exactly what he would have seen if there was no real black hole there. It is true that he does not see her cross the horizon till the point where he crosses the horizon, but that's okay. I mean, nothing special happens there.
What's the view from the other perspective?
Which other perspective?
From Alice looking back to Bob.
We just did that. Here's Alice. Here's Bob. Alice looks back and sees Bob, sees Bob, sees Bob. Nothing special until she hits the singularity, and then she doesn't see anything anymore.
But is there a sudden clarity? Like basically when Alice is just outside, all the things that have fallen in before she did are all smeared on the horizon. And all of a sudden she gets to the other side. Now she sees chairs and dinosaurs.
No, she doesn't see anything. She doesn't see anything sudden happen. Exactly the same as Charlie sees nothing happen to Alice when he crosses the horizon. Doesn't see anything special.
So where's all that matter that she was seeing on the surface before she went across?
As she's falling in, she sees it fall in. As she's falling in, it crosses the horizon. With her. Well, she sees it. She looks back in time. She says, look, she knows that things don't move faster than the speed of light. So she looks back, she watches this stuff fall in, and she says, you know, I know that stuff fell in a long time ago because it's been traveling with the speed of light. Right? So she's not deceived into, well, she might be deceived, but if she knows anything about light, she will know that the stuff fell in before she did. Yeah. Okay. Are we happy? You have the tool to answer any question about this. If you want to know who sees what, just draw the lines and
One final question, maybe. Are you aware of any either movies or fiction that deals with this stuff in sort of a scientifically realistic way?
You mean movies of somebody falling into a black hole? There are, and I don't. You might try Andrew Hamilton. Andrew Hamilton, I think, has made some simulations of what it looks like to fall into a black, what it looks and feels like to fall into a black hole. Of course, you know, I say nothing special happens, but of course, that's right. But the light that's coming at you is coming at you in very peculiar and funny ways, okay? Don't blame me if you watch one of these simulations and get very nauseous. I mean it. I have seen some of them. I can't remember where. They're not very illuminating. You won't get much out of them, but it might be fun to watch one. But they really are disorienting if you're in a big room with one of them in front of you. It makes you seasick. Okay. Let's move on, or should we maybe? Well, we can do one of two things. We can either move on, or we can ask some more questions. But there's something repetitive about the questions that, you know, what does Alice see? What does Bob see? What does Alice see? What does Bob see? What does Alice see? So let's break loose from that.
I think this is a little different question.
Yeah, good.
What's the significance of the apex of the light cone there?
Which one? Where?
Right in the middle.
Here?
No.
Here?
Straight across. Straight across.
Here?
Yes.
Ah. Okay. Nothing much, because in fact, a real black hole that's formed, for example, by stellar collapse or something like that, this isn't even on the diagram. Only a portion of the diagram up here is relevant. So that is where I would go right now if we want to go forward, or next week. This is a sort of idealized black hole, but a real black hole which forms by collapse, only a portion of this diagram means anything, and in particular the part down here doesn't. Yeah.
As stuff falls into the black hole, its mass gets larger.
Its mass gets larger? Why?
Because mass is falling in.
Oh, the mass of the black hole gets larger. Yes, 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 yes. Yes, that's true.
And therefore the Schwarzschild radius is getting larger.
Yes, indeed.
What's happening with the things on the surface there? They aren't.
Which surface? Which surface?
Near the surface of the original surface of the black hole.
You mean the horizon?
The horizon,
yeah.
And is it coming out when it gets bigger? Do they move out, sort of?
The pictures that I drew here were appropriate for Alice's and Bob's, who are much lighter than the black hole and don't have that much the black hole doesn't react very strongly to them. If you were to take, for example, another heavy mass and drop it in and really follow it, what you would see is at first the horizon would bulge out, sort of be attracted by the other object, and then they would merge and form one horizon. Then, because black holes now have no hair, it would pull itself together into a sphere, but the sphere would be slightly larger. And we can calculate how much larger if we know how much mass was added. Remember, the radius is 2 mg. Sorry, 2 mg. So if we add some energy in the form of mass, then the radius responds in an appropriate way. The Schwarzschild radius responds in an appropriate way. Yeah.
There was a recent NASA picture about the center of the Milky Way galaxy absorbing some adjacent matter, but it didn't take infinite amount of time for us to see flashes and so forth.
No. The light that you see from a black hole is not coming from the horizon. It's coming from all sorts of stuff, hot stuff that's circulating around the horizon. And that's heated up by, remember, for example, that at a certain distance around, you can have photons or light just moving around on circles. All sorts of very complicated collisions can take place. We're not, in a real black hole, there's stuff out there. It's not just a black hole in empty space. Here we're pretty much talking about a black hole in empty space. There's all kinds of stuff out there. There's an accretion disk, all sorts of things falling in. And what you see is not really coming from precisely the horizon. It's coming from outside the horizon. So
regarding the mass falling in on the horizon, growing out to meet it, I think you've said previously that the black hole re-equilibrates essentially at the speed of light or something like that.
They equilibrate very, very fast. Almost at the speed of light, yeah. Very, very fast. Right. The time that it would take if you made two solar mass black holes collide so that they formed a sort of dumbbell at first like that, the time that it would take for it to equilibrate is not much longer than the light transit time across it, which is a very small fraction of a second. Maybe 10 or 100 times the light transit time. What's the light transit time across a 1 kilometer black hole? Well, light travels at 3 times 10 to the 8 meters, so 3 times 10 to the 5 kilometers per second. Let's say 10 to the 5 kilometers per second. So 10 to the minus 5 seconds for light to travel across a solar mass black hole. Maybe 10 to the minus 3 seconds, millisecond or something like that, for this great big massive object to equilibrate to the point where it's the shiniest, most perfect sphere that you can imagine.
If you had two very massive black holes starting to merge together, each black hole will not appreciably, I don't believe, affect the shape of the event horizon of the other one.
Oh, so, well, no, of course it will. Yeah. As they come together, the event horizon will look like that. And then it'll look like that. Well, you know what I mean. Peanut-shaped. And then almost spherical, but not quite. And then spherical. All within about 10 to the minus 3 seconds.
Right, but if it's very, very massive, it could take years or longer for the merger to occur. Transit time of light is, if the separation is...
Transit time, okay. If you make the black hole big enough, you can make the transit time across it anything you like. But the biggest black hole that's known, I think, is something like about 10 to the 9th solar masses. I remember that would take about 20 minutes, I think, for light to cross it. So 20 minutes for it to equilibrate.
My question before was really, Bob is looking at something between the original, not the big massive object falling in, but something that it had been falling in and is currently between where the original horizon is and the new horizon, or somehow like, or can it not happen like that?
What will happen if Bob carries, or Alice carries a heavy mass, let's suppose Alice carries a heavy object in and crosses the horizon over here. And what will happen?
No, I'm thinking something else. Martha falls in.
Martha falls in, yeah, good.
And what happens to, what does Bob see happen to Alice?
Where is Alice?
Alice is falling in somewhere else on the horizon.
Here or here? You want it before Martha or after Martha? Before.
It's not really a spatial dimension. you only have one spatial
I know,
dimension.
so we only have that much, we only have a bit of flexibility in drawing pictures. So let's decide, do we want Alice before Martha or Alice after Martha?
Okay, before.
Okay, so here's Alice, right? Okay. Now, we haven't got to the point where we can talk about what happens to the black hole when something falls in, but I will tell you. No, you know, I won't. Keep the question in mind for next week. Okay. Next week, we're going to talk exactly about how black holes are formed, how their horizons form, and if you throw in more material, how the horizon responds, and we will get there. We will get there, and I'll show you. It's surprising. It's different than you expect, but all very logical. Let's come back to it.
How does this diagram change as a function of RS, as a function of the shorts?
This gets bigger.
So the light cones...
Oh, this diagram over here. Yeah. Oh, I see, okay. Well, remember what we did was we scaled out our Schwarzschild. The diagram doesn't change, but the meaning of distances on the diagram changes. The diagram stays exactly the same, but the proper distance, let's say, between this point and this point is proportional to the Schwarzschild radius. So the diagram is exactly the same. It's just like having a sphere. Supposing you had a sphere, two spheres, the moon and the Earth. Well, I can draw them both exactly the same way. They look like spheres. Does the picture change when I go from moon to Earth? No, if I have scaled the radius of the Earth or moon out of the problem. What is true, though, is the same diagram. That distance on the moon might be 100 miles. On the Earth, the same angular distance would be, how much was it, about 4 times bigger, right? Yeah, so on the Earth it would be 400 miles. Same thing is true here. If we had a black hole of a 1 kilometer radius black hole, then this distance here might be, let's say, half a kilometer. On the other hand, we would draw exactly the same picture for a huge 10 to the 9th solar mass, a monster black hole. And then instead of being 0.5 kilometers, it might be 0.5 times 10 to the 9th kilometers. But the diagram would be exactly the same, just the meaning of distances, the actual number of meters, the number of meter sticks connecting those 2 points would depend on the Schwarzschild radius. Just exactly the same as if we took the moon and the Earth, drew exactly the same picture. A sphere is a sphere is a sphere. But then remember that distances between points will scale as the radius of the sphere.
Does anything change if Bob's orbiting the black hole?
No, not much. No, very little. It becomes a much more complicated problem to be quantitative about exactly what he sees, but no, nothing really changes, no. Yeah.
When you have an Earth, something like that, then and you fall in it, then gravity goes to zero because the mass is outside of you. You have a distribution of mass.
No. I understand what you're asking. No. The distribution of mass is not on the horizon.
Mm-hmm. Yeah, it's not on the horizon.
It's not on the horizon.
Yeah.
No.
And so that the gravity then would go to zero, essentially inside the black hole, and similarly to the Earth.
Inside the horizon?
Yeah.
No. No, the time when gravity goes to zero inside an object is if you have a shell of mass and you're inside the shell.
Yeah.
No, there's no shell of mass at the horizon.
No. In a solid Earth, where you have many shells,
mm-hmm.
inside each shell it goes to zero, but then of course you have other shells
mm-hmm.
inside, so
mm-hmm.
the gravitational force as you fall to the center of the Earth
mm-hmm.
goes to zero.
Mm-hmm.
Now how about the distribution of mass inside of a black hole?
It's all at the singularity, all of it. All of it, yeah, all of it. It's like having, it's the analog of having a point mass So that there is no inside and outside.
Except perhaps for travel time in the very recent time.
Except for what?
Travel time in the very recent time. I mean, Alice is not at the singularity until she gets there.
Yeah,
So
you're all right, but you don't get to, if you had a point mass at the origin, you don't get there till you get there. But if you're out here, that doesn't mean that there's no gravity.
Oh, no. But I mean, there might be other masses, the masses which are in the process of falling in.
Oh,
have not
okay,
reached there.
good. We're going to talk about that next time. We're going to talk about exactly that next time. So keep these questions for next time. You're asking about the questions of of the evolution of the black hole as it forms. We'll get there. We'll make a very simple construction of a black hole forming, and you'll be able to see everything happening. So,
There's no way we can even measure the angular momentum of a black hole, right?
say it again.
Is there any concept called like angular momentum of a black hole?
What about angular momentum of a black hole?
I mean, you said, I suppose somewhere you said that if it is rotating fast, then the thing, instead of the horizon being spherical, it can be elliptical. Now, can we actually sense that? I mean,
If a black hole is rotating, its shape is deformed. Yeah, and you can see it from the outside of the black hole.
does gravity changes because it's rotating? I mean,
Yes, gravity changes. Gravity changes because it's rotating, and the whole geometry changes. The whole geometry changes, and if we have time, the rotating black hole is much more complicated than that, and it sort of drags space around with it. Maybe we'll discuss it a little bit, but.
Are you talking about a rotating singularity?
We're talking about material with angular momentum coming together and forming a black hole. Okay, it doesn't lose its angular momentum, and the angular momentum is permanently there. And the effect of the angular momentum is to deform the black hole exactly like the angular momentum of the Earth deforms the surface of the Earth. Makes it into an oblate. I think it's an oblate spheroid. Yeah.
When you say rho depends or is a function of r, are you saying that space away near a big source of gravity is contracted?
No,
it's just the bigger the r, the smaller the rho. In other words,
the bigger the r, the smaller the rho? No. Why do you say that?
It's an inverse function, is it?
It's a function, but
okay. But are we saying that then that the presence of a big source of gravity contracts the space around it? In effect, is that what we are saying?
if you like, yeah. 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 In a sense, that's right.
One more question. Going back to Bob and Alice. From Bob's point of view, Alice's time has stopped. Is it right to say that?
Mm-hmm.
From Alice's point of view.
Well, of course, it depends on.
So the first statement is true, right?
Let's qualify.
Well, it's not true, but it's coming to almost zero, isn't it? It's dilating down to no time. No.
Yes. But let's
it's approaching no time. From
I'm having trouble getting past the horizon.
The question really was, from Alice's point of view, what is space coming to an end for Bob?
No, we draw it again. We draw it again. Here's Alice going through. Here's Bob out here. Stays outside. From Alice's point of view, she sees Bob. Nothing special, Bob. It's just when she gets to here, she doesn't see Bob after that. Not because anything happened to Bob, because something happened to her. That's it. Just draw the diagram, draw the light cones. She sees him over here. Hi, Alice. She sees him over here. She sees him over here. She never gets to see him over here. Again, not because anything happened to him, but because she's no longer there.
Although these should be straight lines, isn't it? Don't they?
Which one? This?
The light from Bob to Alice shouldn't be a straight line. The light would
The
then
light
curve.
from Bob to Alice.
The light going from Bob to Alice is not traveling in straight line. It curves because of gravity then. And
Not in
moves
these
away.
coordinates. Not in these coordinates. Not in these coordinates. In these coordinates, it's straight. In these coordinates.
Like you'd be returning to Einstein's field equations?
Yeah.
Of course.
Yeah. Yeah. They're not as much fun as doing this. Yeah. But of course you have to do them. That's the other side of the coin. Given a geometry and given a solution to Einstein's equations, it's kind of fun to analyze it and to think what people see who are in it and so forth. The other side of the coin is to say, if you had some material, how do you solve Einstein's equations, mass collapsing or whatever, how do you solve Einstein's equations to find out what the geometry is? That's usually a less pleasant exercise. Yeah. Except in some very special cases, and we'll do the special cases.
So what happens to the event horizon for an evaporating black hole? Does it simply just go to zero, approach the singularity, or?
Goes to zero. Well, what happens is the singularity and the horizon merge. Everything just shrinks, and it shrinks down to the point where the horizon just comes in contact with the singularity, and then
It seems like any stellar type black hole would be spinning. Are there thought to be any macroscopic ones that aren't spinning naturally?
Well, that's a good question. Very, very unlikely. How many black holes are there in the universe? Well, there's 10 to the 22 stars altogether. 10 to the 11th galaxies. I don't know. I actually don't know how many black holes there are. But it's somewhere between 10 to the 11th and 10 to the 22. Let's say 10 to the 15th or something like that. Of course, no object is going to have strictly zero angular momentum. When you say zero angular momentum, you mean within some tolerance it's pretty unlikely that a black hole would have such a small angular momentum that you wouldn't notice it. And the reason is this. First of all, stars rotate. Almost anything will have some angular momentum. And when it collapses, you've seen the skater pull the arms in and speed up. Same thing happens when the black hole collapses. Even a relatively small amount of rotational motion will get escalated into a very rapid rotation. So it's very unlikely that there's a black hole out there with such small angular momentum that it would be undetectable.
So is the singularity spinning at an infinite rate?
The singularity of a rotating black hole is different than we've drawn here. The singularity of a rotating black hole is a different thing. So I would say no, that it's not rotating with an infinite velocity, but infinite angular velocity.
We might cover this later on, but are black holes formed by condensation of existing matter, or do they come into existence by quantum nature?
No, they come into existence by stars collapsing, ordinary material.
So it's existing matter that collapses, and that's the
gravity. When a star runs out of fuel, the thing which is supporting it and keeping gravity from contracting it is the heat flowing out through it. The heat flowing out through it is created in the interior of the star by burning hydrogen or helium or whatever it is. When the star eventually runs out of fuel, the forces, the radiation pressure that's keeping it from collapsing disappears, and it contracts. Now, depending on how heavy it is, it might contract to a white dwarf. That's a more or less ordinary thing. It's pretty dense, but it's still made up out of nuclei and atoms and so forth. If it's yet heavier, it might collapse into a neutron star. That's a very, very compact object, but it can still support itself. The material is still strong enough to support itself against gravity. If it's yet heavier, then it can't support itself against gravity, and it just goes and falls past its own Schwarzschild radius. Once it falls past its own Schwarzschild radius, then it's doomed. Once any part of it, or once a part of it gets within the Schwarzschild radius, then it just collapses.
I have a question. I've heard speculation about the existence of micro black holes.
Speculation.
What's the theory for how they form?
There is none.
Okay.
Wouldn't it be great if they were there, though? Because the reason it would be great if they were there, depending on their size, the time scale for the evaporation of a black hole is very, very long, extremely long. It's faster for small black holes and slower for big black holes. If you would like to see a black hole evaporate, it better be small. And so if black holes were formed, in particular, a black hole of about the mass of Mount Everest or something like that, would have a lifetime before it completely evaporates, which would be about the age of the universe. So if there was a mechanism to form such black holes, we might be seeing them evaporate now. Now, it's very hard to imagine, given a mass the size of Mount Everest, there's simply not enough mass there to cause it to contract and collapse. The whole Earth will not form a black hole. The Earth is not heavy enough to do very much of anything when it cools down. The Sun will not form a black hole. At least it's not thought that it will form a black hole. It's thought that it will form a white dwarf. So what would be the mechanism for creating these things? You could imagine very violent things happening in the early universe which would smash stuff together. So it wouldn't be there are two things that you could think of that could help create a black hole. One is making a thing so massive that it contracts under its own weight, that it collapses under its own weight. The other is just motion, velocity. Velocity can replace gravity and slam stuff together. And if there was enough violent, what we want to say, contracting stuff, it could form a black hole, even though it wasn't massive enough to do it on its own.
So could you form one in a particle accelerator? I mean, conceivable.
What kind of particle accelerator?
I mean, is there any conceivable...
The smallest black hole that makes any sense is a black hole of about a Planck mass. That's about 10 to the minus 5 grams. To create particles colliding with that much energy would, if you were to take slack and just lengthen it, you'd have to make it about as big as the galaxy or something like that. But yes, in principle, the answer is yes. In principle, by slamming particles together hard enough, you could make a black hole.
We're going to get into the Einstein equations and how that relates to expanding universe and dark energy, dark matter, that kind of stuff.
Was that a question?
Pardon?
Was there a question there? I couldn't
Yeah,
tell.
are we going to be talking about those kind of things?
Yeah.
Similar question, is there going to be time to talk about entropy at all?
Not this quarter. I don't know if we'll even get to the things that gentleman said this quarter, but we'll see. We go where we go. If not this quarter, next quarter.
Do you already cover gravitational waves?
Maybe not.
Are we going to cover those?
Can't tell. I can't tell. We go from week to week, and however much. I got about a quarter done tonight that I intended to. Right. But that's fine. I mean, it's good. It's good. I don't regard that as a problem as long as everybody is learning something. Okay. we're ready to go.
For more, please visit us at stanford.edu.